Hey folks, today I'm going to be talking about microcalorimeter arrays. And a calorimeter just being something that measures thermal energy, and we want to measure the thermal energy imparted by photons. And so the way that this is done is that a photon absorbing material is placed in contact with a temperature sensor, and when a photon imparts its energy on this, it raises the temperature of that system to a certain degree. And that temperature data is recorded as a spectrum for the target that's being observed. And so this is similar to a bolometer in that it's measuring thermal energy imparted by light, but it's measuring individual photons rather than an area of radiation. And so these are really important cutting edge detectors for X-ray spectroscopy because they have a very high spectral resolution in comparison with previous methods, which that's going to be useful in determining Doppler shift and redshift for things like accreting material on supermassive black holes, because they emit X-rays, and if we can get Doppler shift data on that, we can know more about systems such as those. So the mechanics of this, the absorber is typically used made of mercury telluride, and it's got a low heat capacity, which means a very small change in energy is going to raise its temperature significantly. And it's efficient at thermalizing these photons. And that's connected to the temperature sensor, which in this case is a ruthenium oxide thermistor. And that material is chosen because it has a very good thermistor properties in about the 0 to 4 Kelvin range. And more on why that range is chosen in a second. So these signals in the thermistor are picked up as voltages by a transistor across the thermistor and sent to the calorimeter analog processor, or the CAP. The CAP amplifies the signal and then sends it to the digital processor. And so that's all that process is, a single measurement. And when it's time to clear out the detector for new measurements, the heat sink refrigerator combo returns the detector to near absolute zero. And the reason it's kept so cold is that it's easy minimizing the noise floor since we're measuring thermal variations, and it establishes the floor value for calibration. So that's a single pixel. Let's talk about how these are arrayed together. The pixel size is much larger than what you would see on a typical CCD. But this is measuring energy, not counting photons. And so the distant X-ray sources have a lower photon flux, so the larger target is optimal for this. The array size of this is typically not going to be greater than 100. Compare that to the millions of pixels in a CCD. In this specific detector here, it's a 6 by 6 pixel array. But these larger pixels result in a comparable plate size to what you would see in a narrow field of view CCD. This smaller number of pixels allows us to read out each individual pixel to the analog processor rather than having to bin and shift everything over, allowing for more instantaneous readout. And so all of these pixels are bundled together in an array, and they're kept in thermal contact with a paramagnetic salt, which is cooled by a tank of liquid helium to 1.8 Kelvin, as a strong magnetic field aligns the spins of the salt. And this is a very interesting statistical mechanics application. Once everything is at equilibrium at 1.8 K and all the spins are aligned, the magnetic field is removed, which allows the spins to randomize, which is an increase in entropy. But that increase in entropy requires energy. And so the energy to increase that entropy is provided by the thermal energy in the salt, which cools it to near absolute zero. And on this picture, if you take a look at the red arrows, they're indicating the connections from the paramagnetic salt to the array, and that's what keeps it thermally connected. Let's talk about the characteristics of the array. The pixel scale, they're very large. They're about 30 to 40 arc seconds per pixel, which, as you can see in the photo, which is a comparison between a Chandra image and a simulated microcalorimeter image, It's a very low spatial resolution, but each of those pixels has got a very high spectral resolution. The plate scale just means that the target is going to be taking up most of the field of view. The spectral range for these is the X-ray range, and this is the range at which a small change in wavelength corresponds to a large change in energy. So wavelength dispersion is kind of difficult to get good measurements of because you can't separate the energy as much. That's why non-dispersion spectroscopy in the form of microcalorimeters is going to be so useful in future missions because it provides so much higher spectral resolution and on the order of like 10 times better. The flagship X-ray observatory right now, Chandra, the resolution is about on the order of 100, but the spectral resolution for microcalorimeter arrays is going to be on the order of 1,000, which gives us up to about 5 electron volts, or sorry, down to about 5 electron volts of resolution, which means that we could distinguish between a 200 electron volt photon and a 205 electron volt photon. So there's obviously noise involved in this. So there's several methods to reduce the noise. Obviously there's other sources of radiation that impart heat to metals, thinking mainly infrared. So there's filters that block everything except X-rays. Those filters can't keep out cosmic rays, which also produce a response in the detector. So the solution to that is an anti-coincidence detector, or an antico. If a particle passes through the microcalorimeter and then through the antico below it, it's going to record on both of those, and then we know to throw out that measurement because it was not an X-ray photon. Another worry or problem facing these detectors is a vent pileup, which I guess is sort of comparable to saturation of a pixel. This is just because the cool down time for each pixel is about 80 milliseconds. So if you have a photon coming in and then 20 milliseconds later another one, it's going to stack that energy on top of the pixel, and it's not going to be able to cool back down to the threshold level. So this would mean that they're not resolvable in terms of their energy level. So the first solution to that is to provide a neutral density filter to reduce the photon flux, just have fewer photons coming in, hitting that area per unit time. And the second one is a data processing method, which is event classification, which basically sorts through the data and finds the events that are occurring more than 70 milliseconds apart for the really high resolution. And then for the less resolution, the lower resolution uses events closer together. The last problem is thermal noise and crosstalk, which is just mainly minimized by keeping the temperature at near absolute zero. The thermal crosstalk is where the pixels would transfer some thermal energy to their neighbors. This is mitigated by insulating them and having a separation between them. So the first ever calorimeter launched into space was the NASA X-ray Quantum Calorimeter, the XQC, and it was a suborbital rocket flight, and its target was a pretty easy one. It was just the cosmic X-ray background, so they didn't have to do too complicated pointing. It was a single 240-second exposure, and it provided the below spectrograph, which was a really successful use of this technology. And actually, we were able to reuse the instrument in another suborbital flight 3 years after the original flight. The next one was the X-ray spectrometer. That was aboard the Suzaku satellite by JAXA. It was doomed by a liquid helium leak, which was really, really tragic because it was sort of the flagship of microcalorimeter arrays. But the liquid helium leak meant that it couldn't cool itself to near absolute zero, and it was a useless instrument. So the next calorimeter sent to space was the SXS, which was another low Earth orbit observatory, this time aboard the Hitomi satellite. And this was basically NASA's improved version of the XRS. It was also doomed. The satellite guidance system malfunctioned and caused it to spin faster and faster until it broke apart, and it was a tragedy. And so the last example I have is another suborbital rocket flight. It was the Northwestern University's Micro-X, and the target was the Cassiopeia A supernova remnant. And the mission went great except for the pointing system. They missed the target, and so all of their data was not from the target. But the detector survived, so that was partial success, and it was able to demonstrate the technology once again in a more recent day. So the overall lesson here is that spaceflight observatories have a really high failure rate. Having an observatory and putting on a rocket and having to manage it with robots is just orders of magnitude harder than a ground observatory, but that's the only place that we can observe X-rays. So this is a really promising frontier, but the progress is limited by space launches. And so that brings me to my conclusion, and I will, I guess, take your questions this week. Thank you all so much. Cheers.